Welcome to Math 1400, Nunez Community College. In this section, 1.3, we'll be dealing with right triangle trigonometry. Right triangle trigonometry is basically the trig that you had when you were in geometry class. We start out with having a right triangle. We know it because of the right angle. We have an angle theta. And if there's an angle theta, we know that the side farthest away from theta is known as the opposite side. The side that is touching the angle and the right angle, or in the box, is known as the adjacent side. And the side that's not touching the box at all is known as the hypotenuse. Now, from geometry, we should have known that there was the trig functions where the sine function represented the length of the opposite side over the length of the hypotenuse. We had the cosine. Cosine of theta was equal to the adjacent side over the hypotenuse. And we had the tangent. And the tangent of theta was equal to the opposite side over the adjacent side. Well, now in trig, we introduce the other three functions, which are reciprocals of the three that we see. So we have the cosecant, and that would be the reciprocal of the sine, or the hypotenuse over the opposite. For the cosine, the reciprocal is the secant. The secant is the hypotenuse over the adjacent. And then the reciprocal of the tangent is the cotangent, and the cotangent is the adjacent over the opposite. So we're going to use these facts along with the right triangles in order to tell the sine of the angles, cosines of the angles, tangents of the angles, etc. Example number 1 says find the values of the 6 trig functions given that we have a right triangle with our theta, with one side being 3 and one side being 4. Well, in order to achieve all 6 functions, we need to have all 3 sides, and we're only given 2. So we must find a way to find a third side. In this case, we're going to use the Pythagorean theorem. The Pythagorean theorem. Pythagorean theorem is the a squared plus b squared equals c squared, but I like to use the leg squared plus the leg squared equals the hypotenuse squared. Because in a right triangle, the sides that touch the box are known as the legs, and the side that does not touch the box is the hypotenuse. I put it this way because if not, I found that students always are looking to find the hypotenuse, are always looking to find c squared, even if c happens to be one of the other sides besides the hypotenuse. So we're going to put our numbers in. This is a leg, so that's 3 squared, plus the other leg, which is 4 squared, equals the hypotenuse squared. 3 squared is 9, 4 squared is 16, equals the hypotenuse squared. To give me hypotenuse squared is equal to 25. Well, I don't want the hypotenuse squared, I want the length of the hypotenuse, so I'm going to take the square root of both sides. If I take the square root, I get that the hypotenuse is equal to 5. And by the way, when using the square root method, I know we say both plus and minus, but we can't have a negative length of a side, so we only use the positive. So positive 5. Now we can use what we have here to do the 6 trig functions. I have the sine of theta, this theta, opposite over hypotenuse, which is going to be 4/5. The cosine of theta, adjacent over hypotenuse, it's going to be 3/5. And the tangent of theta, opposite over adjacent, it's going to be 4/3. We can then use the cosecant of theta and do the hypotenuse over opposite, or we can flip the sign, which will be 5/4. The secant is going to be the flip of the cosine, 5/3. And the cotangent is going to be the flip of the tangent, which is 3/4. So in this, we're going to more than likely be given 2 of the 3 sides. We're going to have to use the Pythagorean theorem to find the missing side, and then we're going to find the 6 trig functions. For the next one, we're considering having 2 triangles that are different sizes, but they're similar as in they're proportionate. So if I have 2 triangles, suppose this one with theta here is 7.5 and 4, and the larger one is going to be 8 and 15. We want to find the 6 trig functions of both. If we find that they are proportional, we can just do the larger one with the whole numbers, and that would be sufficient. So since 7.5 multiplied by 2 is 15, and since 4 multiplied by 2 is 8, we can conclude that the larger triangle is 2 times the size of the smaller one, meaning that all 3 sides would be proportional to all 3 sides of the larger triangle. So we only need to find the missing side of the one, and then we can find the 6 trig functions. This one happens to be 8 squared plus 15 squared equals the hypotenuse squared, because we're looking for the hypotenuse once again, giving me a total of 64 plus 225 equals the hypotenuse squared. If I add these 2 together, I get what? 289 equals the hypotenuse squared. And I take the square root and I come up with the hypotenuse is the square root of 289, which comes up to be 17. Once I have this, the ratios will be the same, so I'm going to use the ones of the whole numbers, or the big ones. So I have the sine of theta is going to be equal to 8/17, opposite over hypotenuse. The cosine is going to be 15/17, and the tangent is going to be 8/15. Again, opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. The cosecant, 17 over 8, reciprocal. The secant is going to be 17 over 15, the reciprocal. And the cotangent is going to be 15 over 8, the reciprocal. In the next example, it says, sketch the triangle. And you know we're dealing with right triangles, so we're going to sketch a right triangle. Sketch the triangle and find the remaining 5 trig functions. So they're going to give us one of the trig functions. We're going to sketch the triangle, and we're going to find the remaining 5 trig functions. Okay, so they're giving us, in this case, the sine of theta is going to be equal to 12 over 13. And it says, sketch the triangle and then find the remaining 5 trig functions. So if I want to sketch a triangle, it's going to be a right triangle. Where we have theta, and the sine is going to equal 12/13, and we know that the sine is opposite over hypotenuse. So the opposite side is going to be the side farthest away, and the hypotenuse is here. We're going to have to find this side or that leg in order to do the remaining functions. So I have the sine of theta is given 12/13, which means I also know that the cosecant of theta is the flip, or 13/12. I want to look at the cosine, the tangent, the secant, and the cotangent. But in order to do that, I have to find my missing side. So, in this case, we have x squared, which is the leg squared, plus 12 squared, which is the other leg squared, equals 13 squared, which is the hypotenuse. So that gives me what? X squared plus 12 squared is 144, equals 13 squared, which is 169. Subtract the 144 from both sides. X squared equals 25. Take the square root, and x equals 5. So once we put that in, now I can find the rest. Cosine adjacent over hypotenuse, 5/13. Secant being the inverse, a flip, so that's 13/5. Tangent, opposite over adjacent, 12/5. And cotangent, the flip, 5/12. One thing that might be important is if you would memorize or know some of the, what I call golden right triangles. That's right triangles where all three sides are whole numbers. There are an infinite number of them, but there are certain ones that are used many, many more times than the others. So we'll start off with the one with the smallest whole numbers, which is a 3, 4, 5. 3, 4, 5 right triangle. We did that one in one of our examples, 3, 4, and 5. If I double this, I would get 6, 8, 10. And there's any derivation of that, triple it, quadruple it, and so on and so on. But this is used a lot, the 6, 8, 10 right triangle. This one here is the 5, 12, 13 right triangle. 5, 12, 13, okay? We have another one, which is the 8, 15, 17 right triangle. We did that one in one of the other examples. And then we have the 7, 24, 25. These triangles here are most commonly used. And if you do have two of the sides with one missing, if you know the golden ratio, then you'll be able to use that instead of doing the Pythagorean theorem. Just a little something to memorize if you're into memorizing that. We're now going to have the fundamental identities, fundamental trig identities. These are things that we're going to need throughout the course itself. So these are basically the rules at which we're going to follow. And these are called the fundamental trig identities. The first ones that we have are going to be called the reciprocal identities. And we've already used them when you heard me say the term flip. We used them, but this is what we have. So it's the reciprocal identity. Okay, and that one says that the sine of theta is equal to 1 over the cosecant of theta. It's always hard for me to write the cosecant. And vice versa, the cosecant of theta is equal to 1 over the sine of theta. The cosine of theta is equal to 1 over the secant theta, and the secant theta is equal to 1 over the cosine theta. The tangent theta is 1 over the cotangent theta, and the cotangent theta is 1 over the tangent theta. Those are the reciprocal identities. More identities that we need to know are the quotient identities. The quotient identities. When you hear the term quotient, you think of what? You think of a fraction, and that's what we have. The sine of theta, the tangent of theta is equal to the sine of theta over the cosine theta. And the other one is the cotangent theta, and that's equal to the cosine theta over the sine of theta. Those are the quotient identities. Another biggie is the Pythagorean identities. The Pythagorean identities. Well, Pythagorean theorem, a squared plus b squared, or leg squared plus leg squared. So whenever you hear Pythagorean, you think of squared. And it is the sine squared theta plus the cosine squared theta equals 1. This is the one used a lot, probably 90%. You also have 1 plus the tangent squared theta equals the secant squared theta, and 1 plus the cotangent squared theta is equal to the cosecant squared theta. Those would be the Pythagorean identities. And then finally, we have the cofunction identities. The cofunction identities. And that says that the sine of theta is equal to the cosine of 90 minus theta. When we did the unit circle, you notice that the sine of 30 degrees was 1/2, and the cosine of 90 minus 30, which was 60 degrees, was also 1/2. So that's what it is, the cofunction identities. The sine of theta is equal to the cosine of 90 minus theta. Or the cosine of theta is equal to the sine of 90 minus theta. The tangent of theta is equal to the cotangent of 90 minus theta. And the cotangent of theta is equal to the tangent of 90 minus theta. And lastly, we have the secant of theta is equal to the cosecant of the 90 minus theta. And the same thing, cosecant of theta is equal to the secant of 90 minus theta. Those are the cofunctional identities. The next thing I have is a little something that you need to, or you can remember from geometry. It's with the special right triangles. It's with special right triangles. And the special right triangles are triangles that have the angle measure of 45, 45, 90, 45, 45, 90 right triangle, which would look like this right triangle with a 45 and a 45 and a 90. In this case, since it's a 45, 45, 90, the two angles are the same, so it's isosceles. So the two legs are the same size. And we have a hypotenuse. And with the 45, 45, 90, if you have one and the others are missing, there's a formula. It says that the hypotenuse is equal to the leg times the square root of 2. Hypotenuse is equal to the leg times the square root of 2. The other special right triangle we have is a 30, 60, 90 degree right triangle. Again, that one would look like this, where we got a hypotenuse. This is a 30-degree angle, by the way, and this is a 60-degree angle. But on this one, we have legs that are two different sizes. We have a short leg and a long leg. So for this one, we actually have two formulas instead of one. It is the hypotenuse is equal to the short leg times 2, or that the long leg is equal to the short leg times the square root of 3. And we're going to use that to solve some of the missing parts of triangles. The next part is going to talk about finding the values of some missing parts. So we're going to look at them, and the good thing is both triangles are going to be the special right triangles, so we'll be able to use the formulas in order to solve that. Okay, we're given a triangle, and it is a 45, 45, 90, okay? And they're saying that we have one side is 3. We're trying to find the other two sides. One is listed as an R, one is listed as an X. So the first thing that we should know is with a 45, 45, 90, the two legs are the same size. So 3 happens to be a leg. So therefore we know automatically that X equals 3, because it's the other leg. It's the other leg. In order to find the R is the hypotenuse, so we must use our formula. The formula is the hypotenuse is equal to the leg times the square root of 2. So therefore, the hypotenuse, which is R, is equal to the leg, 3, times the square root of 2. And that would be our other side. 3 square root of 2 and 3. And on the next example, we have a 30, 60, 90 right triangle. And this time we are given a side of 18. We are finding Y and R. Y and R, exactly, we're finding X and R, sorry. X and R. And we have to look at it and determine which side are we given. We're not given the hypotenuse, we're looking for that. We're not given the long leg. The long leg is opposite the longest or the biggest angle, the bigger angle. And the short leg is opposite the shorter angle. So we're given the short leg. We got the hypotenuse and we got the long leg. So now we're going to have to use both of the formulas. In order to find the hypotenuse is equal to the short leg times 2. So R, the hypotenuse, is equal to the short leg, 18 times 2. So therefore, R, the hypotenuse, is 36. And lastly, the long leg is equal to the short leg times the square root of 3. We have the short leg is 18. So we got X is equal to 18 times the square root of 3, which is 18 square root of 3. And that concludes this section, which is section 1.3, right triangle trig. I will see you at the next one.